Okay, good morning, everybody. 2020 just won't give up, will it? A storm coming. I think we're going to be all right, but just can't seem to catch a break, so I'm ready for 2020 to be over. You should never wish for time to go away, but I think this year we'll make an exception to that rule. But as I saw on Facebook the other day, 2020 going away will be admitting 2021, which is kind of a joke. But, anyway, so today we've got several things that we're going to cover in terms of videos and some reading assignments that I gave you all to look at. The first, of course, is our interview with Dr. Roberts-Badon. What was the takeaway message from what you viewed in that particular discussion? Mac?
Don't give up just because the major is hard or something like that. Just because some of your friends kind of easier classes for the major.
Yeah, and easy is always a relative thing, right? I mean, I think there are majors that most students would say are harder than others. I think chemistry is probably one of those that gets there. Polymer science is there. Physics is certainly in there. Math is certainly in there. But again, if you think back to what Neil deGrasse Tyson was talking about, that science is hard, right? It's because we're learning new things. We're really advancing our knowledge and understanding of the world, the universe. And I know that sounds very hyperbolic, but I mean, it's true. We are learning in chemistry how to take the elements that we have been provided in nature, and we're learning how to manipulate those. And we're learning how to manipulate those to make things that we take for granted every day. Materials, plastics in your car, plastics in your computer, in your cell phone, new electronic materials, things that aren't organic. TVs used to be these big things, and now we have materials that allow TVs to be, pretty thin. And all of that is because of science in general. I mean, but of course physics and chemistry play a large role in those types of things. And so, yeah, don't give up just because your major is hard. Let me rephrase that. What was Dr. Badon's first experience in her chemistry class? Was it a large success? No, she struggled early on, right? Went to high school, and I'm just paraphrasing here, but I'm betting she was the student in high school that was able to breeze through everything, and then came to college and was kind of shocked with that first exam in chemistry. And I imagine several of you are in that boat as well, but she persisted, right? She took a very positive attitude about it. She knew what she wanted out of the major. She knew that she wanted to go to medical school. She stuck with it and ultimately did very well and is very successful, right? What else did you take away from the interview with Dr. Badon? Damien?
Learn how to manage your time, like you said, she was talking a lot on other activities other than just her major, and just learning time management now would be good.
Yeah, that's right. I mean, so time management is definitely a big part of people's success. You will find people who are successful that don't have good time management skills, and I would say that is by and large just one of those things in nature that happens. But I would say people who actually are kind of self-made in terms of their success, if you will, are usually successful because they're persistent, are usually successful because I think they have a growth mindset and don't let small failures get in the way of their future success. And I think they have a way of prioritizing, and you can think of prioritizing as another way of time management, but they prioritize their success. They prioritize the things that they know are going to make them successful. And I certainly think that Dr. Roberts-Badon was one of those individuals. I mean, she was probably, let me put it to you this way. I can't think of another student that was more active than Dr. Roberts-Badon and Jessica Flynn, those two individuals that you've already seen. And they both were involved in just about everything. You might recognize Dr. Roberts-Badon. She was Miss Mississippi. She competed in the Miss America pageant. She played the violin. She took a year off between graduating here and medical school as part of that Miss America or Miss Mississippi agreement. She had to do all those things, but she was able to do a lot of different things because she was able to prioritize and know what was important to her at various stages of the game. And so she was able to take advantage of a lot of opportunities. She's also a Goldwater Scholar, right? And so we have the National Competitive Scholarships Office here at the University of Southern Mississippi that is actually housed in the Office of Scholarships. I'm trying to get her to come and talk to us about that. But those types of awards, we've got resources here on campus that can help you get those awards. And so if that's something that you want to do, you need to prioritize that. If you wanted to do a Goldwater Scholar, you wanted to be a Goldwater Scholar, what would you have to prioritize beyond your classwork? What did she do? Research. You got to get involved in research fairly early, right? Many of you are freshmen in reality. You may have sophomores in terms of your hour title. Some of your transfer students, I know. You can all compete for the Goldwater Scholarship. But in order to have a competitive Goldwater Scholarship, you need to have some products from some type of undergraduate research. That's one of the reasons why I'm showing you the interviews with faculty as well, right? Because you need to know who you might gel with, so to speak, and want to do research with, whose topics might be of interest to you, that kind of thing. So yeah, Dr. Roberts-Badon, very, very successful young woman, graduated here, top of the class, went on and did medical school, is now, she's graduated from medical school. She does have her MD. She's in her residency portion of it, I think, if I remember right. And so she is definitely involved in a lot of things. And even though she's not an MD, PhD today, as she mentioned in her interview, she still does some research projects, right? Being a physician, whether you would get an MD, PhD or not, being a physician is like being a scientist. And I know there are some physicians that disagree with my take on that, but when a physician goes in and talks with a patient, they are really using the scientific method, whether they think about it that way or not, right? They're formulating a hypothesis. They don't call it a hypothesis, right? But they're making an observation, they're forming a hypothesis, and they test that hypothesis. How do they test the hypothesis? Pardon? Yeah, some sort of prescription or some sort of procedure, right? You come in, they think you've got, let's stay away from COVID, but you come in, you've got some sort of illness that's going around. They think, all of the symptoms kind of point to that. They give you a course of treatment. Maybe it's an antibiotic. That's the test. They are testing that hypothesis. They're going to have you come back. They're going to have you get checked out again, and they're going to see whether or not that course of action worked. Okay, so there is a lot of relevance to the training that you get in doing undergraduate research for those of you who want to go to medical school. It's going to be important to you, I promise. Okay. Any other takeaways from the interview with Dr. Roberts-Badon? No? Okay. Next was the interview with Shelby Dickerson. Shelby was an honor student, just like Dr. Roberts-Badon. I taught both of these students when we still taught honors organic chemistry. I taught that for several years. Excuse me. And so I got to know these two individuals very well. What was kind of unique about Ms. Dickerson? Damien?
I know she was scared to do a lot of stuff, like before she actually did it, she was like really scared to do stuff.
Yeah, and I'm really happy that Shelby shared that all with you. Shelby was probably, and I don't think she'd mind me saying this, she was probably the most shy and introverted student I'd ever met. And she was also one of those students that I think had a huge potential if I could get her out of her shell. But she was a very timid individual. She did not challenge authority at all. I'm not saying you go out and fight authority, okay? But I'm just like, she was very much so the typical introvert, shy individual. And slowly she came out of her shell and she developed into a very, very excellent scientist. Okay? And so I think that's, to me, she was an extremely brave individual for doing that. It's very easy to be afraid of something and avoid it. She was afraid of a lot of things because of just, her inexperience. But she kind of, with a little bit of help, she really did face her fears, right? She was, extremely afraid of public speaking. And as she mentioned, when she was working in my laboratory, we were gonna go to the Mississippi Academy of Sciences meeting, which was actually hosted here at the University of Southern Mississippi, which was kind of convenient for us. She had some good research results, and I said, go present at the Mississippi Academy of Sciences. And she came back, she wrote her abstract, and as far as I can remember, she said, I want to do a poster. I want to do a poster. And I said, no, you're not going to do a poster. You're going to get up and you're going to talk in front of a group. And the Mississippi Academy of Sciences, it's not a big national meeting where you might be talking to 500 or 600 people. It's about like this classroom, about 20, 30 people in a room listening to what you have to say. I thought it was a good opportunity for her to get in front of a smaller audience, people that she didn't know. Okay? And for those of you who have ever seen a poster presentation, they're great experiences. You put a poster on the wall, basically. You stand by it. People come by. They ask you questions. But it can be a passive experience. You could be there and just answer only the questions that you're asked. Whereas in a talk like this, you have to prepare in advance. You have to be prepared for whatever might come your way. You just never know. And so I told her, I said, no, you're going to do a formal talk. And that really scared her. But she practiced more than anybody as an undergraduate that I've ever seen. She made appointments with me to go over her talk. She made appointments with the other students in the laboratory. Hey, can you come listen to me give the talk real quick? Because it was only about a 12-minute talk that she had to give. She practiced and practiced and practiced and practiced and practiced that talk. And she honed it down very, very well. And she went and she gave that talk, and she won first place in the oral student division for that particular meeting. So here was a person that just a year or so before was extremely introverted. You couldn't get an answer out of her if you asked, kind of situation, to really opening up and moving into the ability to talk at length about her research project. She became confident knowing that she was the expert in the area. And people would ask her some tough questions that I didn't know the answer to. And I'm not saying that she knew all the answers, but she was able to handle that question without freezing, and she did extremely well. What else was kind of unique about her situation? How many research experiences did she have as an undergraduate?
Wasn't it 3?
Yeah, she had 3 research experiences that she talked about anyway, right? She started off doing research in Dr. Wallace's lab and did some inorganic work, and then figured out that really wasn't what she wanted to do. It wasn't anything personal with Dr. Wallace. It was just, she just wanted a different project. So she came and did research in my lab. She wanted to do some organic work. She thought she wanted to go to graduate school for organic chemistry, right? But she also did a third one. What was the third one?
The computer chemistry?
Yeah, so she did a computational chemistry project as an REU student. I believe it was at the University of Memphis. Right? And so she went to the University of Memphis one summer. It was actually a little more than, I think she said it was about a month. It was actually, I think, 2 months. She got paid. She did computational chemistry. She really enjoyed that experience because, as she mentioned in her interview, she liked chemistry and she also liked what other subject? She liked math. She really enjoyed mathematics. And so that computational chemistry experience for her that summer really allowed her to work with math and chemistry within a computer environment, and she studied molecules in the cosmos. She was doing kind of cosmochemistry kind of work from a theoretical basis. And all of that led to her confidence to actually apply to graduate school. And as she mentioned in her interview, again, she went from this very introverted individual to, they gave her an opportunity to be at graduate school to be an instructor of record for an organic class. Okay? Now, organic chemistry typically isn't as large as Gen Chem, but at many universities, well, at least when I took organic chemistry at university, I had 300 people in my class. Okay, so they are typically fairly large classes, very similar to Gen Chem. They allowed her to go and be the instructor of record and handle a class of, maybe up to 300 students. I don't know how big the class is, but a big section class as a graduate student, And so, again, that just, I think, shows you the progression that you can undergo if you're willing to practice, if you're willing to face your fears, if you're willing to stick with it and persist. And there's really no better story in this series for that than I think than with Shelby. Shelby, is a very bright individual. She had some fears, she had some anxieties, she had some introvert qualities, and she was able to come out of her shell, like I said. And so a very good story of a student ultimately reaching the success. She mentioned in her interview that she thought when she was here that she wanted to be a college professor, right? Through this whole trajectory that she's been on, now that she's been able to go in and teach a large section, she's changed her mind. She's actually looking for jobs in industry for a number of reasons. But one of those reasons is that, I did the professor thing. I got the experience. I thought it was what I wanted to do. I now know, I think I want to get a job in industry and try that out for a while. So your career trajectories as you move from undergraduate to graduate school to ultimate job can change over time. You will evolve. What you think you want to do today can and will evolve. Even if you ultimately do the thing that you want to do, things will change. Dr. Roberts Badon wanted to go and be an MD, PhD. Ultimately, she decided to give up on the PhD part and just go the MD route. Things evolved. Things changed. How much time you want to devote to something will change as you mature. And so it is perfectly fine, is what I'm trying to tell you, to allow your goals and your desires to change over time as you go through this educational process. It's part of what learning is all about. What you think you want today may not be what you ultimately want in the end. Anything else? Anything of note that anybody wants to bring up? Okay. All right, that brings us to our research opportunities with Dr. Donahue. You all had an opportunity. I know some of you actually viewed this before it actually became assigned to you, at least according to the views on YouTube. And so that's fine. I know some of you have asked me about opportunities to do research with Dr. Donahue. How would you describe his general theme? And don't say organic chemistry. But how would you describe his general theme? What's he trying to do, ultimately?
Synthesizing molecules.
Okay, he is trying to synthesize molecules, but that could be lumped into just organic chemistry. Beyond that, what's he trying to synthesize these molecules for, if you will?
Drug research.
Yeah. So medicinal chemistry is really kind of his thrust, and that has an awful lot of organic chemistry to it. It has what we call total synthesis, right? So how do you take a molecule that you find in nature and synthesize it from simple starting material so that you can make large quantities of it so that you can ultimately test it for its biological properties and or produce enough of it to actually have a drug. It's very, very important in medicine that we be able to synthesize molecules that we find in nature. And you might be thinking, well, you know what, if you can find them in nature, why do you have to synthesize them? Just go harvest it, right? Why might we try to synthesize the molecule as opposed to just going and harvesting the molecules?
To get a more pure sample.
Okay, purity, absolutely, that's a possibility. What else?
Or maybe because the one found in pure nature might not be good to consume.
That's true, so it might be impure enough that you couldn't really consume it very well.
It might be more cost effective to just synthesize it and try to go out and find it.
It could be more cost effective than trying to grow it and harvest it. All of those are good things. There are a number of reasons why we want to actually do total synthesis. There's the pure academic side of it, which is, can we make what nature has made? Putting our skill set against Mother Nature. We're always trying to do that. Chemists are a little cocky that way. We try to outdo Mother Nature in a number of areas. But also we try to understand how Mother Nature made it. So understanding the biological processes that underwent that the organism or whatever utilized to make the molecule. So that helps our understanding of the biology if we understand how things are actually put together. But also what you'll find is that actually a number of molecules in nature that have biological activity are present in such small quantities that you would have to do huge harvests to get enough material to say, or to treat a patient, for example. A perfect example of that is not on this slide, but it's actually Taxol. Taxol is one of the most potent anti-cancer drugs that we know of, especially for things like breast cancer. And it comes from nature. It comes from the yew tree. And it is present in such small quantities that to harvest enough to treat patients, you would actually have to wipe that species off the face of the earth. Okay, you'd have to cut down every tree and harvest it to get enough material. Obviously, we're not going to do that, right? So we isolate this stuff from nature. We figure out what its structure is. We figure out what its biology is. And then we try to figure out how can we make it from things that we have in abundance, right? We've got a lot of crude oil. We can get organic molecules. We can take those molecules, we can put them together through reactions. We can make the molecules that then are druggable, okay? So there's a lot of that going on. And so total synthesis is about a lot of that, right? Organocatalysis. How can we catalyze a reaction, right? What does catalysis mean? What does catalysis do?
Lowers the activation energy for a reaction, so basically just makes it easier for that reaction to take place.
That's right. So catalysts, at their very definition, speed up a reaction, right? They allow a reaction that would occur normally to occur much faster. We all depend on catalysts. You have catalysts in your body that you typically, biochemists refer to as enzymes, but they're just catalysts. Okay? So to speed up a reaction, absolutely. But there's also things that you can do with catalysis that are beyond just speeding up the reaction.
Well, in air quotes, speeding up the reaction, that would also be making it more favorable, so you would be able to get a certain product over others.
Correct, yeah. So we quite frequently use catalysts that will speed up the reaction that we desire over like some sort of, competing side reaction, as we like to say. Sometimes a molecule can go down two different paths, and you want to speed the one up that ultimately gives you the product that you're interested in, right? And so we're not going to get into all of those details, but we can use that kind of concept to not only put the atoms together like we want, but to put them together in the right orientation. We want the atoms sticking in certain directions in space, and we can use catalysis for that. And Dr. Donahue uses organocatalysis, which means he uses organic molecules to speed up other reactions. Okay? A lot of the catalysts that you probably have heard about in your Gen Chem class, if you've talked about that yet, are metals. Metals are typically used as catalysts as well. The problem with metals are typically toxic. They're not as good for the environment. They don't degrade. And so having an organic catalyst that can actually be biodegradable and recyclable in that sense provides some benefit. Okay? And then, of course, the medicinal chemistry part, which is really, I think, if you want to think about the overall theme, and so he's working on these HIV integrase inhibitors. Who else was working on HIV integrase inhibitors? Dr. Pigza, that's right. So Dr. Pigza and Dr. Donahue both collaborate on that project with Dr. Jacques Kessel, who is our newest biochemist in the unit. And he kind of has a technique for studying the activity of this HIV integrase, which is apparently important in, or potentially important in a target to treat HIV infection. And so all of these things come together under his umbrella, if you will. You're also going to get a variety of techniques from the Donahue Research Group, just like with the Dr. Pigza group. And of course, you don't know all of these techniques yet. That's okay. But nuclear magnetic resonance, which is the organic chemist's best friend, high resolution mass spectrometry, being able to determine a molecule's atomic mass accurately, X-ray diffraction, elemental analysis, high pressure or high performance, depending on which definition of the P you want, high performance liquid chromatography, gas chromatography, infrared spectroscopy, polarimetry, and other things. You're going to leave that research group with a lot of skills that are actually quite marketable. And one of the things that I would say is a benefit of working in the Donahue lab, maybe over a lab like mine, is Dr. Donahue actually spent time in the pharmaceutical industry before he came to the University of Southern Mississippi. So he worked for companies like Wyeth, some pretty high-hitting pharmaceutical research groups doing a variety of different projects. So if you're thinking about, I would like to take my skill set and get a job in the pharmaceutical industry, I would highly recommend you consider Dr. Donahue as a potential research mentor. He's going to be able to give you those types of insights, if you will, that, quite frankly, I wouldn't be able to. My whole career has been academic, and so he's got some things there that he's going to be able to help you with in that regard. Anything else interesting to you all about what Dr. Donahue talked about? Okay. All right, and then we've got another CNEN talks with. I believe I'm going to pronounce this wrong, so I'll just call him Nia. Drug discovery innovator. This is a Merck guy that works at Merck, and he's using synthetic chemistry to understand the fundamentals of biology. What was the central theme of this entire piece with him?
He had someone close to him pass away from sickle cell in Nigeria, so then he committed his life to basically finding cures to diseases like that.
Yeah, so he's on a mission, isn't he? He's got a mission, and he's going to use science to address that mission. What else is kind of interesting about this particular individual?
target with
Yeah.
the drug.
Absolutely. I mean, his central premise, right, is that we've got a lot of small molecules, we've got a lot of drugs. But what I found interesting about his statement was that he claims that a lot of the time we're actually pursuing the wrong biology, right? We think we know what the target is. As an example, a receptor of some sort on the surface of a cell, right? And we test all these drugs and we find things that might work. We find things that work maybe not so well, maybe things that don't work at all. And you go back and you try to think about that, and why is that the case? And he's saying maybe it's the other stuff around it. Maybe we're looking at the wrong biology, right? And so he's using synthetic chemistry to actually target that, to start looking at what else is around that we might be able to go after and see whether or not we can improve drugs, right? And so he was, the central idea of maybe we're looking at the wrong biology, right? That's a profound question if you really think about it, because that can take you off on a tangent that could be very unproductive. But if it is successful, it could actually be quite revolutionary, can't it? And so he's really challenging kind of the status quo way of thinking about how we approach medicinal chemistry. And so, I found all of that very, very interesting. Of course, I was very drawn to this as well because he did his PhD at Vanderbilt University. That's where I did my postdoctoral work, so I'm very much so a Vanderbilt fan. He was not there at the time that I was there. I left in 2004. He got his PhD in 2011, so he would have come to Vanderbilt probably 3 or 4 years after I left. So never got to meet him, but nonetheless, we have that kind of thing in common, at least a common geographic point. His favorite type of reaction is known as click chemistry. Anybody know what that might mean? What does it sound like? Yeah, in a way, that's right. I mean, so if you think about it, have you ever played with those magnetic kits that you can build structures out of? They click together, right? And if you take two pieces and you click them together, you make one piece, right? And there's nothing left over. Most reactions actually have byproducts, right? You react A plus B and you get C plus D, and C is what you want, and D is a byproduct that you have to dispose of. In click chemistry, it's A plus B gives C. So every atom that was in A and B came together to make C. And that is the most efficient way, if you really think about it, from an atom's point of view, of making molecules, right? If I can take a trainload of substance A, a trainload of substance B, and get 2 trainloads of product and not have to throw anything away, companies want that, right? And so we call that click chemistry. It's a general term that was very, very made very famous by a Nobel laureate, Barry Sharpless, many years ago. And there's several different kinds of click chemistry, but it's kind of the hot, it's not as hot as it used to be, but it's kind of the hot word that floats around in science circles these days, is how can we take all of the atoms that we have, put them together to give us the product that we want with no waste. And so it's kind of a hot topic, if you will. All right. So I have this book called The Chemistry Book. It's about this thick. I highly recommend, if you like just reading general stuff about science, that you buy that book, especially if you're a chemistry major. It talks about things going back to ancient times up to the modern day, essential events, essential discoveries, essential concepts that really change the way that we think about the world. Okay? And they're basically 2-page kind of things, a 1-page overview, like you see here, and then kind of a photograph of the contributor or the time period, whatever the case may be. I find myself, when I'm at the computer for far too long during the day, I'll take a break and I'll pick up the chemistry book and I'll just thumb through it. And I'll, trying to understand a little bit more of the history of the science that I call my profession. Okay? I think it's very important that you have some grounding in that. So for the rest of the semester, every time we come to class, there will be a couple of these things out of the chemistry book that I want to share with you. Things that I think are very important for you to have a very good grasp of, not only functionally but historically, because these things change the way we think about things. And one of those is acids and bases. Okay? In fact, I think this is so important that I have argued in my unit in chemistry that we could devote an entire course to acids and bases and rethink the way we think about general chemistry. I think a lot of times we throw an awful lot at you in general chemistry without really distilling it down to its essence, and I think acids and bases are the essence of chemistry. If you have a good understanding of acids and bases, you really understand about 95-96% of everything you need to know for organic chemistry, for analytical chemistry, for biochemistry, and all of biology. Okay? And I know that may seem, again, kind of hyperbolic. He's kind of blowing it out of proportion, but I really don't think so. Especially with the theory of acidity that was devoted in this particular section. What theory was this one really talking about? What kind of acid theories have you learned about? Have you learned about the different acid theories? We've got Arrhenius acids, we've got Bronsted-Lowry acids, and we've got Lewis acids. And the Lewis acids, in my view, is the most important theory for you to really understand. Okay? G. N. Lewis came up with this theory in the early 20s, and it really revolutionized the way that we think about chemistry. When you get into organic, you will understand that most of the reactions that you are asked to memorize or asked to learn or asked to reproduce are really nothing more than a series of Lewis acid, Lewis base reactions. Okay? A Lewis acid is an electron pair acceptor, and a base is an electron pair donor. And when you get into organic chemistry, you'll say, I'm pushing this pair of electrons to this atom. That is nothing more than a Lewis base reacting with a Lewis acid. And so if you have a firm grasp of Lewis acidity and Lewis basicity, the world just opens up to you. For me, it really was an opening, an awakening of my understanding of organic chemistry. When I first took Organic Chemistry 1, I struggled with memorizing all the reactions. I don't memorize very well. It's almost like I stick something in, something else pops out. Okay? But once I understood that everything that I was really dealing with was nothing more than a series of Lewis acid, Lewis base reactions, I can keep that in my head pretty well. And I can do the chemistry. Okay? And so G. N. Lewis, kind of a tragic story in a way. He contributed more than just Lewis theory. What else has Lewis's name? Can anybody think of anything else? Lewis structures. And what are Lewis structures about? Electrons, right? They're about electron pairs. How do you put the electrons around an atom? Right? And in doing so, we can start thinking about how molecules are shaped because of electron pairs. And structure equals function, right? He really did start to solidify the idea that chemistry was all about the electrons. The nucleus was there just as a placeholder for the electrons to orbit around, if you will. Okay? Now that's an oversimplification. But in reality, all of the chemistry that you do is because of the electrons. Okay? So very, very important. And so he had a role in how bonds were angled from one another, distanced from one another in Lewis structures. He came up with his Lewis theory of acidity. He looked at the Arrhenius theory, which was about being a proton donor or a hydroxide donor when placed in water. And he said, but there are things that aren't protons that act like acids. There are things that act just like bases but aren't hydroxide. Bronsted-Lowry came in and said, we'll think about it as a proton donor or a proton acceptor. If you donate a proton, you're an acid. If you accept a proton, you're a base. And again, Lewis said, that doesn't explain all of the things that function like acids and bases. And he realized that it was really all about the electrons. And so, in just 3 years, Lewis acid, Lewis base theory will be 100 years old. And it still accounts for just about everything. Yes, there are people out there that have refined the Lewis theory, but the Lewis theory itself, I think, was the most revolutionary acid-base theory that we have. Okay? It explains why DNA interacts, the bases interact. It explains hydrogen bonding. It explains why reactions work in organic chemistry. Okay? So again, a very, very important discovery. Looking at the picture on the other page, what's the problem with this picture? Yes?
No PPE.
No safety glasses. Back in the 20s and earlier, people went into the lab without wearing personal protective equipment. We're a lot safer in the lab today than we used to be. I know when you all go to lab, you all get frustrated with your goggles fogging up, especially when you have to wear face masks. I get it. But this is no joke. Safety is no joke. In fact, G.N. Lewis died in his laboratory because of a lack of PPE. Some say it might have been suicide even when he was 70 years old. I don't know if that's true. So I'm not going to throw him under the bus with that. But he was found dead. And he was found dead because he was working with cyanide. He was working with hydrogen cyanide, liquid hydrogen cyanide. And it's been hypothesized that what happened was a tube broke and he became overwhelmed with the fumes and died. I mean, hydrogen cyanide is the gas that they use in the gas chamber. If you've ever heard of somebody being put to death in a gas chamber, it's HCN, that's the gas that's used for that. It's a very, very potent killer, if you will. But organic chemists still work with liquid hydrogen cyanide. I don't in my lab. I stay away from it quite a bit, but it is used. And today we have things like respirators. Obviously, we require you to wear safety glasses, but we also have efficient hoods. Back in the 20s, people were doing all of this chemistry out on a bench top in a room like this, breathing these things in. And so, unfortunately, he came to the end of his life in his laboratory, presumably due to a laboratory accident. So safety has come a long way in these 100 years as well. Another thing that I think you all should know about G.N. Lewis is he was nominated for the Nobel Prize well over 40 times and never won. And I think it's a shame. Because when you think about it, especially from a general chemistry point of view, his name is probably the one you hear the most. Lewis structures, Lewis acidity, Lewis basicity, right? And he was nominated many, many times for the Nobel Prize and never won. And there were a lot of gossip going around that I've heard over the years that, he really wasn't a particularly nice guy. I don't know if that's true, and the Nobel Committee held that against him. I really don't know. But what I can say is that, in my opinion, Gian Lewis deserved a Nobel Prize, and he certainly mentored, I think, at least 3 recipients of the Nobel Prize. So at least 3 people that worked with him, mentored and got mentoring from him in their research, ultimately went on to win the Nobel Prize. So I think, that's just an interesting tidbit, that a lot of people who get nominated for the prize quite frequently don't win the prize. There's one other individual that you will learn about as you get up into some of your higher level chemistries. His name was F. Albert Cotton, and a lot of people believe that Cotton should have got the Nobel Prize, and he did not. But he was kind of in similar company with Gian Lewis in terms of his contributions to chemistry. Anything that you want to add about the acids and bases piece? Yeah.
I wanted to ask if you were talking about the Lewis base and Lewis acid theory. Would that be if we're in Gen Chem right now, would that be in our textbook, or would we have to look somewhere else?
No, it's in your textbook. Typically, you don't get into acids and bases until the end of 106, I think. And then certainly in 107 you talk about it. But again, I think in my personal opinion, acid and base theory is the thing that probably should be taught very early on and should be taught in every class you ever take. It's that important, in my opinion. I think some of us as chemists blow it off too much, but I think if you have a good, solid understanding of Lewis acid, Lewis base theory, you can answer a lot of questions with just that simple concept and understanding what it means. I think that's very, very important. All right, the last chemistry book piece for today was on the chemical bond. And this is actually for Dr. Pauling. Professor Linus Pauling, and the book says, probably considered the greatest chemist of the 20th century. I think there's some truth to that statement. Again, I would put him on par with Gian Lewis in a lot of respects. Certainly Pauling changed the way that we think about chemistry. Thinking about how bonding occurs, how 2 atoms actually hold on to one another. That's a very powerful concept, just like acidity and basicity is. How do you take 2 atoms and how do they stay together? How do they remain bound together? Until the 20th century, really most of the chemistry that was done was just guesswork. Chemistry wasn't always the science that it is today. Okay, there's a reason they called some things alchemy. Okay, but understandings of things like the bond, the fact that 2 atoms can actually share electrons, and those electrons are holding those 2 atoms together to be in a lower energy state, is a very, very important concept for you all to know. Okay, it's as important as Lewis acidity and Lewis basicity, okay? And so Linus Pauling worked very hard in a number of areas. He was trained kind of in the quantum realm. He learned about quantum physics in Europe, brought that information back to the States where he taught, Berkeley, right? And really develop that in a way that we can think about chemistry very practically. You don't really have to have a complete understanding of all of the mathematics behind chemistry to really have a functioning knowledge of it. And that's, I think, what he showed, is that if you understand bonding, you can really do things without having to do the strict mathematical approach that a lot of physicists use in their descriptions of things. And so he was really responsible for helping us understand that orbitals on an atomic scale can actually hybridize into new orbitals and change the shape of things. When you all get into organic chemistry, you'll study carbon. And if you look at the Lewis dot structure just for a carbon atom, it doesn't explain why it's tetrahedrally shaped. Pauling helped change our understanding of why it's tetrahedrally shaped, that orbitals can actually mix and hybridize, as we say. You'll learn about that kind of stuff. Have you all already talked about orbitals some in Gen Chem?
Yeah.
Yeah. So you're learning some of that, right? And you're learning that an orbital is nothing more than a probability of finding an electron within a given space. But if you were to look at carbon as it's set on the periodic table, it would have right angles, 90 degrees, and it wouldn't have 4 bonds, and it would, why does it have 4 bonds? Why is methane CH4, and why does it look like a tetrahedron? Pauling helped us understand that. And so he won a Nobel Prize for his work on chemical bonding. He also worked out how proteins form helices. An interesting story there was he figured that out while he was ill. He was at home sick in bed, and he got some strips of paper. And I don't know what possessed him to do this. He started drawing down the primary structure of a protein, putting the atoms down on these strips of paper. And he started playing with the strips of paper, and he realized that if you twist it, every so often there's room for a hydrogen bond. And so he was able to figure that out by being sick and being bored and playing with strips of paper, that it's this hydrogen bonding that accounts for the shape of some proteins. And so he was a very, very active scientist for a number of years. Won the Nobel Prize in chemistry, and then won a second Nobel Prize for what? Peace. That's right. He was a big proponent of disarmament during the Cold War. I don't know of all of his activities in that realm. I don't know ultimately what led to his Nobel Peace Prize in that. I've never really studied that piece of it. But he's one of just a handful of folks that ever won the Nobel Prize twice, and won the Nobel Prize in chemistry solo, which doesn't happen as often as you might think. Okay. This past year, how many people won the Nobel Prize together? 2. Last year, I think it was 3. The year before that, it was a few people together. So if you go back through that Nobel Prize list that I had you put together for the last 10 years, you'll notice there are multiple recipients on those awards, right? But not in the case of Linus Pauling. Linus Pauling lived to be, I think, 92 or 93 years old. He was also a big proponent of vitamin C. Another contribution that he made. A lot of people thought he was getting kind of in the realm of quackery later in life with this, but he was famous for taking several grams of vitamin C every day and believing that it was going to promote a lot of health benefits. And in fact, vitamin C is very, very important. If you have vitamin C deficiencies, you get things like scurvy. You can die. Vitamin C is an important antioxidant. So he wasn't wrong in a lot of his descriptions of vitamin C, but I think it's a situation where people have challenged his notion of you need to take multi-grams a day of vitamin C are probably overblown. But again, just to kind of show that a scientist can have Nobel Prize winning activities in multiple areas, and then they can, also kind of get into the skeptical area where or speculative area where they're speculating on the importance of a vitamin, something like vitamin C. And he had very little evidence to support his claims at the time, so it wasn't particularly overly scientific. Okay. So what do you think about the chemical book or the chemistry book topics? Include some more?
Please.
Okay. So we'll have a couple of them. They're not hard to read. Pretty straightforward. And so with that, I think I'm going to give you 5 minutes left, and we'll call it done for today. Your attendance assignment is available now, and of course the notebook reflection will be due by 11:59 tomorrow, as always. None of that's being changed because of the coming storm, unless we get super hit with something. But then I'll be in communication with you if things change. But for right now, everything is as normal, and I will see you all next week. Please exit out the back.